Continue with our work problems. Now maybe you can remind me because it was a couple days ago, but what does work equal? How do we calculate work? What's the physics definition of it? Force times distance. Good. Force times distance. That always kind of bothered me. Now we don't have the nice big heavy calculus textbooks like we used to, but I used to kind of demonstrate something kind of funny about this definition. I would give one of my student volunteers a heavy Calc 1 book, or calculus book really, and ask them to hold it out at arm's length. And then I would just wait, and after a while their arms start shaking because they're getting kind of heavy. And I say, well, by the laws of physics, you're not doing any work because there's no distance. You're not moving anything. But still, so it feels like there's something lacking in this definition, but it's not ours to argue right now. What we're going to work on is finding how much work is done pumping out this tank full of water. Now the description gives us this tank with a certain radius at the bottom, at the top, and a height. So the height is 12. What you're going to need to do in a lot of these problems is come up with a coordinate system to help you with this sketch. So for myself, that's going to start with putting 0, 0 here at the bottom. Now 0, 0 is here at the bottom, and I've got a radius of 3. What are the coordinates of this point over here?
3, 0.
Yeah, thank you. Thank you, Brandon. 3, 0. All right. Now let's move all the way up to the top. This point has coordinates of what? 0, 12. And then if I move a distance of 6 over here, what are the coordinates at that point going to be?
6, 12.
Yeah, 6 and 12. Thank you. 6 and 12. And it's important to get all these points lined up because we're going to need them as we work through our problem. Now what we're going to imagine is taking a slice through this little figure and just think about the work done in moving that one really thin slice. So we'll start with our slice like this. I'm going to draw it kind of a little bit curved to match the container that it's in, although it's really just a nice horizontal slice. Curtis, what's the thickness of that slice?
dy.
Nice, dy. We're taking a horizontal slice, so it's going to be a dy thickness. We're going to find the force on that one slice, or force required to move that one slice, by calculating essentially its volume. So the force to move one slice. Well, that force is going to be the density times the volume. And the volume's a little bit different in this case. For the volume is going to be the area of this times the thickness. Area times dy. Well, what's the area of this slice? I mean, if you kind of looked at it, moved it around in your mind, what kind of a figure is this slice going to draw out for you? Or what's the area of this cross section? Pi r squared. Thank you, Brandon. So pi r squared, so it's going to be rho times pi r squared times dy. Now that dy is a nice clue for us. Gina, what's that telling us relative to the rest of our problem? What's that dy saying? When we set up our radius, yes, we got to keep that in terms of y. So, all right, let's think about this much then. I'm going to just put a spot over here, call it x and y, and I need to come up with an expression for that radius because that's going to help us out with our area formula. So I need to know what r is. Now, one way to think of r, if you wanted to give this coordinates, it'd be 0 and y. The radius is just this horizontal distance, x minus 0. So the radius is x minus 0. But Gina just told us that we wanted to do this in terms of y. So, okay, we're going to have to do a little bit of thinking here. This is where these extra points are going to come in handy. We need to come up with the equation of a line between these 2 points. So, all right, that's a little bit of a pain, but it's certainly something doable. So, a couple ways you can do this. One thing that you're going to need, first of all, is the slope of that line. Slope is going to be your y2 minus y1 over x2 minus x1. I'm just going to call this my x2, y2, and this is my x1, y1. Those are the points I'm going to use to find the equation of the line between these 2 points. So let's see what I get when I fill it in. That's going to be 12 minus 0 divided by 6 minus 3. 12 minus 0, difference in the y's, over the difference in the x's, 6 minus 3. So basically 12 over 3 gives me a slope of 4. Okay. Now it's up to you how you want to finish the rest of this. One easy way is to use this formula, y minus y1 equals m times x minus x1. And since I've got a very friendly point in terms of x1 and y1, I'll use that. That's going to be y minus 0 equals 4 times x minus 3. So we'll put in those 2 points, 0 and 3. And it looks like the equation of my line is y equals 4x minus 12. So that's kind of the real big pain about this problem. The rest of it I don't think is terribly bad. But we had to solve this equation, or find this equation, after we set up our points. So let me pause here for a second. Are we okay with what we've got here? James? Yeah. Not okay? Oh, you're okay? Okay, all right. Anika? Doing good? All right, well, going back to Gina's observation, we need to solve for r in terms of y. So we need to solve this for x so that we have an expression in terms of y, not an expression in terms of x. So I'll move the 12 to the other side, becomes y plus 12. That's going to equal 4x. I'll just divide both sides by 4 right away and get this expression for my radius. That's your radius. Nice. Question?
I'm confused. What does that say?
Y plus 12
Okay.
over 4 equals x.
That's a 12. Okay.
Sorry if that's not terribly legible. Let's see if we can't fix that a little bit for you. Y plus 12. There. All right, let's throw that into the equation up above. And that's going to give me rho times pi times this thing squared times dy. And that thing squared is my y plus 4, or excuse me, y plus 12 over 4. I'm going to clean that up just a little bit. 4 squared is 16. I'll take that 16 out in front, along with the rho and the pi and the 16, and just leave behind y plus 12 squared dy. All right, so there's the force. There's the force to move one such slice of this little figure. Let's see how far we move that slice. Now we're taking this water and we're going to pour it out as a spigot at the top here. So it just has to go up to this height. Doesn't matter exactly where, but we're just going to go up to this height. So the distance that it moves is going to be this point minus this point. So this point has coordinates of 0 and 12. So what's the distance between these 2 points? Now let me try and, let's do this for you. That's D. That's what we're trying to find. Next, D for distance. What's the distance between the top of my figure and that slice? Yeah, 12 minus y, right? When you're looking at the distance between two coordinates, it's either top minus bottom or right minus left. In this case, it's the distance vertically, so 12 minus y. Nice. So we've got our distance right here, and we've got the force right here. Let's put those things together and try and figure out how much work would be done moving these or pumping out all the water from this tank. So work is going to be force times distance, so it's going to be this times this. So the work done to move one slice is going to be this. It's going to be force, that's going to be work is going to be force times distance. So typo here, W equals force times distance, which is going to be all this times this. So rho times pi divided by 16 times y plus 12 times 12 minus y. That y plus 12 is squared. And then there's going to be a dy in here as well. So, wow, not too bad overall. There's the work done in moving exactly one slice. All right, pretty good there. But we're not just going to pump out just one slice here. We want to drain the entire tank. So to do that, we're going to add up the work that's done in moving all these such slices. The mathematical figure that does that for us is the integral. So it's going to be the integral of rho, which is 62.5. Let me put that in whenever. Over 16 times y plus 12 squared, 12 minus y dy. What are our limits of integration? Where is this going to be integrated from and to? Yeah, 0 to 12. The lowest that you can take this slice is 0. The highest that you can take this slice and still be in this tank is 12. So 0 to 12. Nice. Now there's one other nice thing about this. Take a look at the integrand. What kind of a function is this? It's polynomial. What have I said about polynomials? Fn int. All right, so you can finish this much with Fn int, but right now we're looking good for that one. Comments on example C here? Anything that maybe I went over a little too quickly, laying out? Hannah? Yes.
Writing like steps down to get like from the beginning where you started from.
So writing steps down, I guess I could probably categorize them in terms of some major steps. So the first thing to do is define the force to move one slice. So that'd be kind of a first step here for me in all these types of problems. So, general steps. First of all, characterize the force to move one slice. Let's see. That's actually got a couple little parts, because a lot of times you might need to come up with an equation to help you find that. So that's going to be a big challenge. Let's see. Calculate the distance that slice will travel. And then find your limits of integration. And then use f and int or find the antiderivative. So finish with f and int or an antiderivative. Now, like I said, step one really contains a lot of work there. And I'm sorry that I wasn't, because you kind of caught me off guard here a little bit with that question. But for step one, there's a lot of little parts there in step one to characterize the force on that. If you look back, what I first had to do was I had to have a pretty good sketch of what was going on there in terms of that tank, right? We had to put in coordinates, and we had to figure out the equation of this side, and then solve for x in that equation in order to come up with our expression for y, our expression in terms of y, and then plug it into our formula. There's a lot that goes on here. So that's going to be the big challenge. When I grade these things, I mean, if I had to try and guess this right off the top, if this was like, say, a 10 or 12 point question, let's go with 12. I'd say this is like 7 points. This would be another 2 points, 2 points, and then we'll call it 1 point and 2 points. So the big task for you lies in this first part, setting up the integrand. And that's going to involve a little bit with the distance. I don't think the distance is too difficult, but it is going to require some thought, and we are going to practice that distance part of it in example D, which is just a little tweak on this one. So I hope that helps out a little bit.
No, it does, yeah.
Okay.
Could you go back one more time for the fourth step? What does it say?
Finish with fn int, which is your calculator's version of finding this numerically, or an antiderivative, meaning you have to actually integrate it by hand with finding an antiderivative and then finish it up that way. James?
So for these problems, we're always solving for work, right?
Yeah, I mean, there's a different variation on this. The first problem that I skipped last time, but yeah, there's a spring constant type problem known as Hooke's law that we can work on with those. If we get a chance, we'll do one today. If not, I'm not going to worry about it. These types of work problems are more of interest to me. Okay, let's move down here just a smidge, and we're going to make one change to our problem, but it's going to change our integrand. Let's see if we can finish off that change. This much. Do we want to take a minute and practice our f and int, or are you good with that command in your calculators?
Can we practice it?
Okay. All right. So keep in mind that rho is 62.5. So let's figure out this here, and we'll take a look at it on our graphing calculators. I'm not sure why, but it always takes TI SmartView an extra second or two longer than I might like to open up. All right, while we're waiting. Oh, no. There we go. See, I had to threaten it to get it to work. All right. So let's leave the 62 pi divided by 16, 62.5 pi divided by 16 part off for just a moment. Math 9 is where we're going to go for f and int. We're going to integrate between 0 and 12. Now, oftentimes I like exact answers, so if we do it this way, we're going to get a nice exact answer by leaving off the pi. Now, instead of a y, I'm going to use an x just because it makes life easier. X plus 12 squared, and then another set of parentheses, 12 minus x. And then, of course, you're integrating with respect to x, so dx. There you go, 19,008. Let's see, let's multiply that by 62.5. At the same time, we'll divide by 16. So there you go, 74,250, and the units would be pi. So 74,250. And that would be units of pi. Let's include one more thing here. At least I'll include it. It's optional for you, but that depends if you want full credit or not. What one thing am I missing here that I think I should include as part of my answer? Units. And the units in these work problems are foot-pounds. All right, good question. Does that help? All right, cool. You're welcome. Let's revisit that problem with one change. What if you're pumping to a point 2 feet above the tank now? How does that change our problem? What change do we have to make to our integrand? I'll give you a hint. It's not going to change rho or the 16 out here.
Limits will go from 12 to 14.
Not the limits. Because even though this is being pumped out here, the slices can only be taken in this region. So the limits are still going to be 0 to 12. But I appreciate the thought there. There is one thing that's changed. Brandon.
The force necessary.
The force is still going to be the same because you're still working with the same shape. Yeah. Nika, same thing? The distance? Yeah, the distance. So the force was going to be the y plus 12 squared over 4 squared, which we came out over here. But the distance has changed. What's the distance now that you're 2 feet higher than you used to be? What's this point up here? 0.14. So the distance that you've got to move in order to pump out that slice has changed. So that slice now needs to travel a distance of what? 14 minus y, like that. So that would be the big change, is the distance formula has changed. And the rest, I think you can work that out with f and int like we did before. It should be more work than what we did here because you've got to move that slice a little bit farther. Nice, nice. Okay. Comments on that one? Are we okay with example D? Let's work through example E. So here we go, example E. So sometimes it's kind of a little pain to get all the nice math symbols in here. So I took a little bit of a shortcut here. It just said rho. That's your Greek letter. So we're still working with water. We're going to pump it out of a kind of a trough with a triangular cross section. So our work's going to be kind of similar to what it was a little bit ago, but now we've got a little bit of a different cross section to work with. So let's work with example E, see what can happen. So let's make that 4, 5, example E. And we'll start out, remind ourselves, work equals force times distance. And we'll start by calculating the force. Now, for convenience, I'm going to recopy this cross section here. So the force, that's going to equal the area times the thickness times the density. So it's going to be rho times the area times the thickness. And let's take a look at our slice here. Again, you're going to take a horizontal slice. So we're going to take a slice like this. That's going to be your thickness. What is our thickness for this one? You've got another dy slice. So once again, we're going to have to fuss around with things and solve for things in terms of y. Now the area. Haven't really tried to give you a 3D perspective here. You've got a nice 3D perspective over here. And we're going to pump that out 2 meters above 2 meters above our tank. There's something wrong here. So if we're working in meters, then I should use a different density. Probably should be newtons, I think. Newtons per cubic meter. So you have to pardon me, I don't quite remember that. I think it's like 9,800. I'm not sure. We're just going to Google this. Let's see. There. So, what is the density of water in newtons per cubic meter? Not interested. All right, I was pretty close. I said 9,800. They got 9,810 newtons per cubic meter. So we'll make that change there. So let's write down density is 9,810 newtons per meter cube. All right. We're going to need to find the area of our little cross section. So let me go back up to here and draw ourselves a cross section in our figure. So if we take a slice parallel to the surface there, and parallel here, can you use your imagination to figure out what that slice is going to look like? What's a cross section of this tank going to look like in terms of its area? Yeah, it's going to be a rectangle. So the area of one rectangle is something that I hope and trust that you know. Area is just going to be the length times the width. Length times the width times the thickness, which we already know is dy. Now let's come and label this stuff like we did before. Let's give ourselves a simple coordinate system to work with. I'm going to put the origin of my system here, 0, 0. The height of this tank was 3 meters. So what's that put that point at? Right there. 0, 3. So this is 0, 3. And then the width across the top was also 3 meters. So what's that put this point at? Yeah, 1.5 and 3. Because remember, the whole distance across the top is 3, so half of that distance is going to be 1.5. Okay, looking good. We can put another point up here as well. That's a point at the top. What's that point at the top going to be in terms of its coordinates? 0, 5. Yeah, thank you. 0, 5. So I think we're in good shape there in terms of figuring things out. Now, there is one more thing we're going to need, and that is if I give this coordinate the point, say, x and y, I'm going to need to know how wide this is. So for that, I need to come up with an equation of a line. Let's do the same thing we did last time. We'll start by finding the slope. I'm not going to bother to write the formula this time. It's just going to be 3 minus 0 over 1.5 minus 0, which simplifies to 2. Let's take advantage of something else. Because this is a line that goes through the origin, typically the equation of our line is y equals mx plus b, but I get a pass on the b for this problem, right? Why do I get a pass on the b? It's 0. So the equation of our line is just y equals 2x.
And you can still get that by putting it into the other formula that we used on the last one?
Yeah, you can get that by putting in the other formula as well. There's nothing wrong with using the point slope form of a line. Now in this case we need to solve for x. So what does x equal? Yeah, y over 2, 1/2 y. Either way you want to write it, that's fine. So that's the width. What's the length? The length is going to be the dimension this way. We don't have to do a whole lot of figuring to find out that length. What's the length? Yeah, the length is 8. So I'm going to have 8 times y over 2 times dy. And it's probably worth it to simplify that a little bit. That's going to be 4 times rho times y dy. I think 4 times rho is going to turn out to be, well, you know, rho is now in newtons, so we won't get some nice simplification there. All right, so we got our force. Great. What else do I need? Distance. All right, so the distance. Will, how about the distance? What am I going to have for the distance? Our distance is going to be the distance that this moves. So how far is it between this point here and this slice down here? Well, you want to go down to this point here. X, well, you can call it 0 and y. What's that vertical distance? Yeah, top minus bottom. The difference in the y coordinates is going to be 5 minus y. We okay with that? Okay. Let's put this together to find the force moving one slice. Force, actually the work done in moving one slice, I should say. We've already got the force. So the work to move one slice is going to be force times distance, which is going to be 4 times rho times y times dy times 5 minus y. I'd probably reorder this and clean it up a little bit in order to finally integrate it. So I'll take the 4y out front and leave behind y times 5 minus y dy. Oops, I think that should have been a row. So, whew, work done in moving one slice. Feels like we're doing a lot of work doing these work problems. So, let's finish this one up. So to finish that up, I need to add up the work done in moving all these slices. So, let's see. Rain. The work done in moving all these slices is going to come from an integral. I'll take the constants out front, 4 times rho. What should be my limits of integration for this particular problem? Where do you think I'm going to integrate from and to? Yeah, 0 to 3. Keep in mind, you need to stay within this region, the region defined by our tank, so 0 to 3. So 0 to 3. Nice. Let's bump this one out on fn int. It's just a polynomial. So math 9, 0 to 3. Now you can leave it factored, or you can multiply it out. I'm just going to multiply it out, and I'm going to use it x as in place of y. So 5y minus, or 5x minus x squared dx. Bam. So if I multiply that by 4, that should be 54. And then I need to multiply it by 9810. 9810. Now keep an eye on things. I think WebAssign might just use 9800 for the density of water in terms of newtons. But there you go. So if we're using 9810, we'll end up with 529,740. But what units go with work in the SI system? Well, work is going to be force times distance. Force is in units of newtons. What's our units of distance in the metric system? Meters. So Newton meters. So your answer here would be Newton meters. Nice. All right. Oh no. Oh, my battery must have died. Ah. All right, Newton, Ethan, fill it in for me.
I don't know what the button says.
I know what it says.
Easy.
That was easy.
That was easy.
No, yeah, there you go. There you go. All right, it was not easy. This is like a sad moment. My button died. I'll have to get a new battery for it. Okay, a lot of work on that problem. I'll be happy to go over some of that with you if some of it's still bothering you. It's like, where is that? See a few of you just anxious it could be, like, man, I can't wait to do these things in homework. Yes?
With y over 3 equals x, wouldn't that just be the right half of the limit of x?
Ooh. Yeah, no. Let me think about that. Because in the last problem, we wanted the radius. Yeah, you're right. I think I'm off by a factor of 2. Yeah, because I just treated this as if it was the radius. So that's half of this distance. Yeah, we need to double that. Basically we need 2x, right? X is that distance here, and it's that distance here, so the total width of that would be 2x. So, yeah, that's a bummer. All right, so times 2. There's a nice thing you can do on your graphing calculator. You can just hit times 2. It'll take your previous answer and multiply it by 2. So now we're over 1,000,000. I don't really have a good feel for newtons. I just can't really relate to that. I mean, I like the SI system overall. Times 2. So it's going to be 1,059,480 Newton meters. Yeah, good point. So in the last problem we were lucky because we could get away with the radius, which is why I only used that half that distance in the last problem. But you're right, this problem we got to use the whole distance, which is going to be 2x. So my bad. Nice catch, Kaiser. Thank you. All right. Yeah, so that actually kind of makes it a little bit nicer. If we wanted to have 2x is interchangeable with y, so we didn't even need to solve there, because 2x would be that distance here. X is here, and another distance of x there. If you wanted to see it a different way, if you wanted to find that distance there, if this coordinate is x and y, this coordinate would be negative x and y. And that distance would be x minus negative x. The width of that would be 2x. So x minus negative x equals 2x. That's your width. And from our equation, y equals 2x, so those two are interchangeable. We were off by a factor of 2, so I multiplied by 2 at the end. Thank you. Nice catch. All right, let's move down to example F. Tank is full of water. Find the work done. Find the work required to pump out the water out of the spout. Use 9.8 meters per second for G. Use 1,000 grams. So that's going to give you Newton is 9,800 kilograms per cubic meter. So 1 Newton, the density of water there is going to be 9,800 newtons per cubic meter. Okay, let's look at this one then, and we're going to do the same thing. We're going to be taking a slice and moving it out of the tank here. Let me cut my figure through with a slice, like that. And a lot of this stuff remains the same. Work equals force times distance. Force is going to be the density times the area times the thickness. What's our thickness going to be in this case? dy. So that much is going to be a little bit easier. Now, if this is a spherical tank, then what's the shape of the cross section going to be? If you're looking at a spherical tank, circle. All right. So it's going to be rho times pi r squared times dy. And now we're going to have to get busy figuring out some equations here. So let's do that. And for that, we're going to need to give ourselves a coordinate system. Now, generally speaking, in these types of problems, I've started out by finding the coordinates of one point, actually the coordinates of the origin, and then defining everything else in terms there. Where is it convenient to put the origin in this problem? Yeah. right there in the middle. So that's going to be coordinates of 0, 0. And the radius of this tank is 3. So that gives us an equation of the perimeter of this tank, or the circumference of that tank. What's the equation for that, the circumference of this tank, or that circle? That'd be the distance. But what's the equation of this circle? Circle of radius 3. X squared plus y squared equals 3 squared. Yeah, or 9. So that's the equation there, and that's good. If this has coordinates of 0 and 0, the coordinates here would be 0, 3. And I don't think we're going to need any lines in this one, so might not make a difference. This is going to have coordinates of 0, or excuse me, of x and y, some general point here on my surface.
Isn't that supposed to be 3, 0?
Yeah, 3, 0. Thank you. So we need to find the area, and for the area, I'm going to need this distance. So that's going to have coordinates of 0 and y. So the area is going to be pi r squared. The area of this cross section is just going to be a circle. So pi r squared. This time, unlike the last problem, again, we want the radius. So we don't have to worry about doubling it this time. It's just going to be whatever r is. We need an expression for r. That radial distance is x. So radius is going to be right minus left. Right minus left coordinates is going to be x minus 0. So r equals x. But that's not so good. What's the problem with having r equal to x? You need it in terms of y. So we need to solve for x in terms of y. So it's going to be x squared equals 9 minus y squared. Or better yet, what does x equal? Square root of 9 minus y squared. Now there's something nice and kind of interesting that's going to happen when we put this back into our formula, and that is the r squared is going to cancel out with that root. We could have gotten away with things just here, but it's not always easy enough to anticipate all those things. Square root of 9 minus x squared squared again. Not x squared, how about y squared? And those two are going to cancel each other out. So we'll end up with rho times pi times 9 minus y squared dy. Now it's time for the distance. The distance that this has to move. Now keep in mind we're moving to a height that's 1 meter above the top of the sphere. So what's that height going to be? What's the coordinates of this point going to be if you're 1 meter above the top of the sphere?
0, 4.
Nice. 0, 4. Remember, you're starting out here. You move up 3 to get to the edge of the sphere. You move up another 1. So now at your point 0 and 4. Let's figure out the distance that this thing moves. Write down an expression for the distance and check with your neighbor real quick. See if you agree. So, Amro, how far does this have to move? What's the distance going to equal? No worries, no worries. The distance is going to be the difference between these 2 points. This one at 0, 4 and this one is 0y. So if you subtract, if you want to find a vertical distance, you're going to subtract the y coordinates. What would the difference in those y coordinates be? Marlon? 4 minus y. Are we okay with that, Amro?
Yeah.
All right. Finally, work equals force times distance. The work done to move that one slice is just going to be this times this. So let's see, let's put the rho times the pi times the 9 minus y squared times 4 minus y times dy all together. That's the work done in moving one slice. Let's see, that's going to be rho times pi. So the integral is going to be the integral from something to something of 9 minus y squared times 4 minus y dy. What do I need to integrate between? 1 and 1. Yeah.
4.
I've got 3 different answers. 0, 4, 0, 3, and negative 3 to 3. 0, 3? So let's look at the lowest that we can go here and to the highest. Remember, you want to stay within the tank. So Brandon B, I think it is. What's the lowest that I could go and still be within the range of this tank? Yeah, down here at 0, negative 3. So negative 3 up to where? 3. So you want to completely cover this figure, so negative 3 to 3. Great. Looking good there. Yeah, the rest of it, I would finish with Fn int. All right. Gina? Something in particular? No? You sure? Just take it, just soaking it in. It's like, all right, gonna watch the video when you get home. Anything else on this one? I guess you would finish it up with Fn int. Yeah, I don't see any real tricks. Even though this is a symmetric interval, I don't see any tricks. One thing's for sure. What quality of an answer would say that you're wrong? Can you get 0 here? Would that sound right? Kaiser, you're making me nervous, but I need to hear from you anyways.
It says h equals 1, so it should be from negative 3 to 4.
No, because the tank only goes up to here at 3. So the largest, the tallest that you can get and still have a slice in this tank would be 3. So its limits are determined not by the height. What the height here determines where you're pumping it out. That determines the distance that you move, but it doesn't determine the limits of integration. Your limits are going to come from the tank itself. Yeah, you're welcome.
How do you know the lowest was negative 3?
Oh, because this is a sphere. This is, I mean, the equation of a circle. So if we're starting here with a radius of 3, then you're down here at negative 3. Yeah, no, I appreciate that question. You know, the great thing about you guys asking questions is that there's somebody else that has that same question. And so I encourage that. I hope you guys keep it up. It helps me and it helps your other students as well. And it helps you, of course.
At any point we have to use the data that they gave us, like 9.8, they're talking about gravity, but are we supposed to use it by anything?
So that rho for us in this problem with these two things is going to be 9,800 let's see, newtons per meter cubed. That's what these things are going to combine. So earlier, when we did the previous problem, I used 9,810 because I Googled that. Essentially, they're telling you to use 9,800 is what they're telling you. So appreciate that. Okay. Anything else on this one? All right, let's stop things here.